This is my intermediate algebra course. Today we're going to learn how to solve exponential equations, and we're also going to give an introduction to logarithms. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. In previous classes, we learned the exponent rules and how to simplify expressions with exponents. Now we're going to use the exponent rules to solve equations with exponents. If you don't want to access your files, you can take a picture of these rules with your phone. You're going to need these today, or you can take a screenshot. So we'll get started with exponential equations. These are exponential equations because the variable is in the exponent. The variable is the exponent. Now, we solved equations in previous classes like so. This equation has an exponent, but it's not called an exponential equation because the variable is the base, not the exponent. To solve this equation, we're going to use this property over here. It tells us if you have some number raised to a power, and that expression is equal to the same number raised to a different power, it turns out that those powers must be equal, or exponents, whatever you want to call them. So an example of this may be 7 to the second power is equal to 7 to the x power. The only way that that equation would work is if the exponents are equal. So x must be equal to 2. So it's a pretty obvious idea. It doesn't really need to be explained much. We're going to use that property to solve equations like so. You can tell what the answer to this is going to be. You can actually do this in your head pretty easily. Obviously, x has to be 2 because 3 to the second power is 9. But just to get used to using that property at the right, we're going to go ahead and show some work here. So we're going to change 9 to 3 to the second power. Isn't it true that 9 can be written as 3 to the second power? And now we have that expression that we talked about over here at the right where the bases are the same. So obviously the powers have to be equal. And I know what you're thinking. You're thinking this is pretty easy. And it is easy, but we're going to get into more difficult problems that are going to require this principle here. So we need to get used to it, even though these problems are pretty simple. So I'm going to use that principle again over here. We know that x is going to be 3, but to get used to that principle, I'm going to try to get the same base. That's what we're trying to do here, is we're trying to write expressions on both sides of the equation that have the same base. So I'm going to change 8 to 2 to the third power. Isn't it true that I can write 8 as 2 to the third power? 2 to the third power is 8. So now we have that expression. The bases are the same, so obviously the exponents must be equal. So again, I know that seems pretty easy, but we're going to need that idea for more complicated problems. So I want you to try numbers 3 and 4, and I want you to use this principle here. You're going to take 36 and write it so that it has a base 6, and use it to solve that equation just like we did over here. So try number 3, and when you come back, we'll do it together. All right, we're back. So I'm going to rewrite 36 so that it's 6 to the second power, and you can see that tells us that x must be equal to 2, because again, we're using this principle up here. So do the same thing for number 4. I want you to change 125 so that it has a base 5, and use that to solve the equation. Try number 4, and when you come back, we'll do it together. All right, we're back. So 125 is equal to 5 to the third power. And now that these two expressions have the same base and we know that they're equal, obviously the exponents must be equal. Again, I know you could do that problem in your head without doing any of this work here, but we're getting used to that property above. Okay, so if you got those answers, good job. So now we're going to solve equations that require one exponent rule, and I want you to write the Roman numeral of the exponent rule that you use. And so we're going to start with root 5 is equal to 5 to the x power. So I'm going to use rule number 9, which tells us that square root 5 is equal to 5 to the 1/2 power. The difference is we went backwards. So usually when we use rule number 9, we go from a fraction power to a root expression, but now we're going backwards. We're going from a root expression to a fraction power. So we have the root expression and we're going to a fraction power. So it's the same rules that you did before, used before, but we're just going in the reverse direction. So now we have the same base, 5, and obviously the exponents must be equal. Let's try number 6. So the whole purpose here is to get the same base. You see how we have exponential expressions with the same base, and those expressions are equal to each other. So obviously 16 is not base 2, so I'm going to change 16 to 2 to the 4th power. I'm allowed to do that, right? 16 is the same thing as 2 to the 4th power. So all I did is change 16 to 2 to the 4th power. And now I'm going to use rule number 8, except going backwards. Usually we go from a negative power to a fraction, but now we're going from a fraction to a negative power. And you can see where I'm going here. The bases are the same. These exponential expressions are equal, so therefore the exponents must be equal. We used rule number 8 on that one. All right, let's try one more of these before you try some on your own. So now I'm going to use rule number 6. I'm going to change that 3 to 3 to the 1st power. Any number can be written to the as a number to the 1st power. That was rule number 6, and now you can see where I'm going with this. The bases are the same, so that means that the exponents must be the same. That's the whole point here, is we want to write exponential expressions where the bases are the same. And we can solve that pretty quickly. That's just a 2-step equation. Subtract 4 from both sides, divide both sides by 2, and we get 3/2. Okay, so I want you to try number 8. I want you to notice that these problems here are almost exactly the same as these problems here. So if you get stuck, use the problems above. Remember to write the Roman numeral of each exponent rule that you use, and the whole point here is to get the same base. We want these expressions in yellow here, actually here and here. You see, that's what we're trying to do. We're trying to get those expressions that have the same base. So try number 8, and when you come back, we'll do it together. All right, we're back. So we're going to change that to 9 to the 1/3 power, and that is rule number 9, just like we did on problem number 5, you see. And now you can see we have the same base, so x must be equal to 1/3. If you got that one right, good job. Remember, you can use these problems up here to help you, so try number 9, and when you come back, we'll do it together. All right, we're back. So I'm going to rewrite 49 as 7 squared. I'm allowed to do that, right? I can take 49 and change it to 7 squared. They're the same thing. So then I'm going to use rule number 8, like we did in problem number 6. And I'm going to turn that fraction into an expression with a negative power. And now we have the same base, so we can see that x is equal to -2. Now again, you might be thinking these problems are kind of easy. Well, they are, but they're going to get more difficult as we go along here. So it's very important that you follow along the way that I've been following along here. So these are the important expressions that we're looking for, where the bases are the same. Use number 7 to help you with number 10. And when you come back, we'll do it together. All right, we're back. So I'm going to rewrite 85 as 85 to the 1st power. And we're using rule number 6 there. And now the bases are the same, so x minus 2 obviously equals 1, and x is equal to 3. So if you got that answer, good job. Okay, and again, that was the expression we were looking for there. You know, I think I'm going to change these to green just so it correlates with this up here. Maybe that'll help you. Okay, let's try some different problems here. Now, I want the same base, so I'm going to change that 32 to 2 to the 5th power. So all I did was just change this 32 to 2 to the 5th power. Now, a lot of students at that point would stop there and say, okay, we have the same base. We have 2 here and we have 2 here. Well, actually, not really. This is not base 2. This is base 2 to the 5th power. Okay, so we need to keep going. We need to use rule number 5, which tells us if you're raising a power to another power, you have to multiply those powers. So now, at this point, we have the same base. So we can get rid of those bases and subtract x from both sides. And it's just basic math, and we see that x is equal to 1. So pretty easy. So I'm going to write my imaginary margin here so I can write my exponent rules next to there. So I'm going to use rule number 5 again with this problem. I'm going to rewrite 64 as 4 to the 3rd power. Isn't that true? I know that's kind of a big number, but 64 is the same thing as 4 to the 3rd power. You can verify that on your calculator if you want to. And so now I'm going to use rule number 5. If you raise a power to another power, you just multiply those powers. Now you have to be very careful with the parentheses here. A lot of students would write 3 in parentheses like that, and then 5 plus 3x. That's not correct. You need to multiply 3 times the entire thing. You need to write these orange parentheses here, or it's not going to be correct. Right now, it just looks like you're multiplying 3 times 5 to get 15, but you're not multiplying 3 times the 3x, you see. These little problems really plague students in the math curriculum. So you don't need to write the 3 in parentheses, but you do need to write the 5 plus 3x in parentheses. Okay, so I'm going to move that up a little bit just so there's no confusion whatsoever. Remember, with math, there's these little details that make all the difference. Whenever you're learning a language, math is a language. Whenever you're learning a language, it's very important to get the details right. So now let's multiply. We're going to have to use the distribution property. 3 times 5 is 15. 3 times 3x is 9x. And so now we're at that crucial point where we see that we have exponential expressions that are equal to each other and we have the same base, so we just get rid of the bases. So now subtract 2x from both sides, subtract 15 from both sides, and x is equal to negative 16 over 7. Okay, let's try number 13. One more before you try one on your own. So it's pretty obvious that, if you think about it, it's pretty obvious that this exponent here has to be 0, because if you raise something to a power and it simplifies to 1, the power has to be 0. So what we could do is just jump right down to 0 equals x over 7 minus 5. But just to get used to using that exponent property that we talked about, the green one, the green and purple one up here, I'm going to show some work here and change that 1 to 2 to the 0 power. Isn't it true that 2 to the 0 power is equal to 1? Two to the 0 power is equal to 1. So at this point, you know where I'm going here. We have the same base, exponential expressions that are equal to each other that have the same base. And so the exponents are equal to each other, and if you solve that, we get x is equal to 35. That's just a two-step equation. Now, if you're rusty on two-step equations, you can go back to my pre-algebra course. But that's really just review stuff. If you're having trouble with this basic algebra here, again, you can just go back to my previous courses. When you get into upper mathematics, you don't have time to cover stuff like, by the way, that was rule number 7. Forgot to write the rule number. I know it's hard, but remember, when you go into upper math courses, you're expected to know the stuff you learned from previous courses, even though in reality students forget a lot of it. But again, just go back to my pre-algebra course if you're having any problems with the algebra. So I want you to try number 14. And remember, you can use these problems up here to help you. So you're going to use problem number 11 to help you with 14. So, and remember to write the Roman numeral. Remember, we're trying to get the same base, these green expressions. So try 14, and when you come back, we'll do it together. All right, we're back. So 81, I'm going to change to 9 to the second power. And, whoops, I forgot to write the x. A lot of students would stop at that point and they say, okay, we're done. We have 9 as the base, but 9 is not the base yet. 9 squared is the base. So we're going to have to use rule number 5, which tells us to multiply the exponents. And now we're at that critical point where we have the same base, exponential expressions that are equal to each other with the same base. And so now we can just get rid of the bases. Subtract x from both sides, and we have x is equal to 6. So if you got that answer, good job. Remember, you got to write your Roman numeral there. So go ahead and try number 15. Remember, you can use number 12, and I want to warn you, be sure that you use parentheses properly. You see these parentheses up here in yellow? Be sure you use those parentheses properly. So try number 15, and when you come back, we'll do it together. All right, we're back. I'm going to rewrite the left side of the equation. I'm going to change 16 to 2 to the 4th power. And then I'm going to use rule number 5, which tells us if we're raising a power to another power, we can multiply the exponents. So we have 4 times x plus 1. Make sure you write the parentheses around the x plus 1. You can write parentheses around 4 too also, but you don't need to. But if you write parentheses around the 4 and not around the x plus 1, did I say x plus 2? I meant x plus 1. If you write it this way here, that is not correct. Okay, so now we need to use the distribution property. So 4 times x plus 1 is 4x plus 4. And now we have that critical expression there. So x minus 5 is equal to 4x plus 4. Subtract x from both sides, and we get 3x on this side. Subtract 4 from both sides, we get negative 9. And x is equal to negative 3. So if you got that answer, good job. Okay, I want you to try number 16. Remember, you can use number 13 to help you. And when you come back, we'll do it together. All right, we're back. So I'm going to rewrite. I want to get the same base, so I'm going to rewrite 1 as 7 to the 0 power. And that is rule number 7. And now we're already at that critical point. So we know the bases are the same. So the exponents must be the same. And we get x is equal to negative 2. You don't have to show the work on that because, again, that's just pre-algebra stuff. So if you got that answer, good job. Okay, Let's try a few more problems here. Now this problem, we're not at the critical point because, I mean, we have base 2. You see the base 2 here, we have that, and we have base 2 here, but we have a 4 next to it, which kind of messes things up. So we have to combine that 4 somehow with this expression, 2 to the 3x. Now, a lot of students think that you can take this 4 and 2 and just multiply them and get 8 to the 3x. But we can't do that because these numbers, they don't have the same base. If you wrote 4 to the 1 power, for example, you see that we don't have the same base. You can only combine those if you have the same base. Also, I guess you could combine them if you used rule number 3, but rule number 3 would require us to have a 3x on the 4. Then we could say that that's equal to 8 to the 3x. That would work. But again, we don't have a 3x on the 4, so we can't do that. So what we're going to do is we're going to take 4 and change it to 2 to the 2nd power. And then we're going to use rule number 1 on the right side of the equation. Because we have the same bases here, if we're multiplying powers with the same bases, then we can just add the exponents. That's rule number 1. And so now we're at that critical point. So we can get rid of the bases. We know the exponents must be equal to each other. Subtract x from both sides. Subtract 2 from both sides. And we see that x must be equal to 3/2. Let's try another one of these problems. So this problem is going to use, we have a fraction, and these exponent or exponential expressions, they have the same base. So when you're dividing, rule number 2 tells us that we can subtract the power. So we have 7 to the 2x minus 3 minus x. So we took this power here, this exponent, and we subtracted this exponent. So now we're going to simplify. 2x minus x is just x. And so now we're at that critical point where we can get rid of the bases. Actually, both of these are kind of the critical point, but we just simplified. And so now we have x minus 3 is equal to 10x plus 4. Subtract x from both sides, and we get 9x over here. Subtract 4 from both sides, we get negative 7. And x is equal to negative 7 over 9. All right, so I want you to try number 19. We want to get expressions that have the same base. We have 3 over here and 3 over here, but the problem is the 27 is messing things up here, so we can't really get rid of the bases. So we need to change that 27 so it has a base 3, and then use rule number 1 to combine those numbers into one expression. So go ahead and try number 19, and when you come back, we'll do it together. All right, we're back. So I'm going to change 27 to 3 to the 3rd power. And then I'm going to use rule number 1, which tells us if we have the same base, and we're multiplying powers, then we can just add the exponents. So now we're at that critical point where we can just get rid of the bases, and we have 3 plus 4x is equal to 7 plus 2x. And get all the variables on one side, so on and so forth. We've done this 1,000 times in previous classes. And there you go, so x equals 2. So if you got that answer, good job. Go ahead and try number 20. Use number 18 to help you with number 20. And when you come back, we'll do it together. All right, we're back. So we're going to use rule number 2. That tells us that if we are dividing powers, we can just subtract the exponents. So we get 10 to the x minus 4, and then we're going to subtract x plus 6. Now, a lot of students would forget to write parentheses here, and that spells doom in terms of getting the right answer. Remember, you have to subtract this entire thing. If you just leave the parentheses off, then now you're not subtracting the whole thing. Excuse me, now you're just subtracting the x, and you're adding the 6, so it means something completely different. And I know what you're thinking. You're thinking, I don't like math. I don't like that. Well, it's a language. You have to learn these little details, or else you're going to miscommunicate. That's how language is. You just make the slightly wrong gesture or incorrect writing or speak incorrectly, and it means something completely different. Okay, so now we're just going to simplify. We have x minus 4 minus x minus 6. You don't have to show all those steps, but this is -1. We're using the distributed property, -1 times x, and then -1 times 6. But remember, we don't have to write -1 here. Some of you may be thinking, I already know this stuff, but again, some students forget this, so it's good to go back over this. So the x's are going to cancel out. X minus x cancels out. We get -4 minus 6 is -10. And so now we're at that critical point where we're going to get rid of the bases. So we have -x plus 3 is equal to -10. And then subtract 3 from both sides. We get -13 is equal to -x. Divide both sides by -1, or you can multiply both sides by -1. It doesn't really matter. We get x is equal to 13. So if you made a few mistakes there, that's okay, as long as you know how to do it now. If you got that answer, good job. If you didn't, that's okay. Just figure out what you did wrong. All right, on to number 21. So I'm going to use rule number 3, which tells us that this becomes 7 times 2 all raised to the x power. So remember, rule number 3 tells us if you have the product of two numbers raised to a power, that equals the first number raised to the power times the second number raised to that same power. The only difference is now we're going backwards, you see. For rule number 3, we went from here to here normally, but now we're actually going backwards. Sometimes you're gonna have to go backwards with these particular problems. So 7 times 2, that's equal to 14, and that kind of gives us an idea of what we need to do on the left side of the equation. We need to change that 196 so that it has a base 14, and it turns out that that's 14 to the second power. And I'm not usually going to give you problems that require you to raise such a big number, so don't worry about that. There might be maybe one problem where it's kind of a big power, but we're at the critical point. We see that x is equal to 2, and we're done. So pretty easy. Okay, let's try number 22. Now we're going to use rule number 4. If that just becomes 10 over 5 all raised to the x power. again, rule number 4 tells us if you're dividing two numbers and that fraction is raised to a power, then that's equal to the numerator raised to that power divided by the denominator raised to the same power. We're just going backwards now. So if you're getting a little intimidated by this, by having to use these exponent rules in the forward and reverse directions, that's okay. You're going to get the hang of this as we go along. It's kind of like a puzzle. We're solving a puzzle. 10 divided by 5 is equal to 2. And now we have an idea of what we need to do. We need to change that 16 to 2 to the 4th power. And now we're at the critical stage where we see that the exponents must be equal. Let's try one more of these. In this problem, looks like we're just going to use rule number 10, so that's going to be 4 to the 3/4 power. Actually, no, I'm sorry, it's 4 to the 4/3 power. So that's the critical stage where that was pretty easy. We now see that x is equal to 4/3. And you're done. So that was kind of an easy one there. Okay, I want you to try number 24. Use number 21 to help you. And when you come back, we'll do it together. All right, we're back. So I'm going to change this to 2 times 5 raised to the x. That's rule number 3. Just going in the backwards direction. 2 times 5 is 10. So I change that product to 10. And now I'm going to change 100 because we know we have to have base 10. So I know 100 is 10 to the 2nd power. And we're at the critical stage. We know the exponents must be equal because the bases are equal. So if you got that one right, good job. Try number 25. And when you come back, we'll do it together. You can use 22 to help you. All right, we're back. So we're going to get 56 over 7, all raised to the x power. That's rule number 4. Make sure you're writing these Roman numeral rules. And 56 divided by 7 is 8. So now we have an idea of the base that we need to be looking for. So we need to change 64 so that it's base 8. So that's 8 to the 2nd power. And of course that's the critical stage where we can just get rid of the bases. Okay, so on to number 26. Go ahead and try 26. You can use number 23 to help you. Be aware that this is the different variation of rule number 10. So remember, there's 2 variations of rule number 10. So you might want to refer back to these exponent rules at the bottom there. Try number 26, and when you come back, we'll do it together. All right, we're back. So we have 7 to the 3/5 power is equal to 7 to the x power. That's rule number 10, the variation of rule number 10. And I forget if I wrote a prime symbol. I guess I could write the prime symbol. I forget how I notated that before, but we're at the critical stage and we have 3/5 is equal to x. And there you go. So if you got that one right, good job. All right. Let's go on to some more problems here. So now we're going to do equations requiring 2 exponent rules. So we're starting off easy and getting a little more complicated. So I'm going to change 7 to 7 to the first power. That is rule number 6. Any number can be raised to the first power, or it is considered to be raised to the first power. So then I'm going to change 343 to 7 to the third power. Again, I know that's kind of a big number, but I'm not going to give you very many of those or any at all. Again, a lot of students will want to stop at that point and say, well, we have the same base. Well, actually, we don't have the same base. Here we have base 7, but here we don't have base 7. We have base 7 to the third power. We need to use rule number 5. Keep going, use rule number 5. That tells us when you're raising a power to another power, you just multiply the exponents. Make sure to put the parentheses in the right place. And we can use the distributive property. So we have 7 to the 3x plus 3. And we're at the critical stage. The bases are the same, so the exponents must be equal. And solving that, we get negative 2/3. So now we're going to use rule number 1. And again, notice we use 2 rules on problem 27. So that tells us if we're multiplying powers with the same base, we can just add the exponents. And at that point, we're going to use rule number 7. 4x plus 3x is 7x. I'm going to hold off on rule number 7. I'm going to try to do everything step by step to avoid confusion. So I'm going to use rule number 7 at this point. And then I'm going to make, I know it's going to be 5 to the 0 power because I'm looking for base 5. So 1 becomes 5 to the 0 power. Anything raised to the 0 power is 1. I'm just going backwards now. So now we're at the critical point. And we see that 7x plus 2 is equal to 0. So x must be equal to negative 2/7. All right, next problem. We're going to use rule number 2. So when you're dividing powers, use it and you have the same base. You just subtract the exponents. So we have x minus 2 minus 5x minus 4. And remember, you have to be very careful about where you place those parentheses, or if you use parentheses at all. A lot of students will not use parentheses and they'll get the wrong answer. You're subtracting this whole thing here, you see. All right, so that was rule number 2. So now I'm going to, just doing step by step here, I'm going to simplify. We have x minus 5x is negative 4x, and negative 2 plus 4 is positive 2. Then I'm going to use rule number 9 to make that 4th root of 3 equal to 3 to the 1/4 power. And we're at the critical step. So then we can say 1/4 is equal to negative 4x plus 2. And that's an equation with a fraction. There's a lot of different ways to do it, but I'm just going to use the easiest way. You can use whatever way you want to. At this point, you can do a lot in your head if you know how to solve these equations. You can go back to my class in my beginning algebra course on how to solve equations with fractions. When you get into upper math, When you get into upper math, again, you can skip a lot of steps, but in my beginning algebra course, I showed you the slowest way because that's the easiest way to understand. But once you get into this level, you're expected to kind of speed up a little bit. So you can go back to my class on solving equations with fractions in my beginning algebra course and review that. Okay, so I want you to try number 30. You can use number 27 to help you. I'm sorry I gave you kind of a big number there, but you can use your calculator with the root button on it to figure out what that would be, or just the power button. When you come back, we'll do it together. All right, we're back. So that is going to be 4 to the 4th power. We're looking for the same base. And then we're raising a power to another power. So we just multiply the exponents. Make sure you put the parentheses in the proper position. So that's rule number 5. And I'm going to lower that a little bit just so there's no confusion whatsoever. So now we have to use the distribution property. 4 times negative 2x is negative 8x. And 4 times negative 3 is negative 12. So now I'm going to use, you don't have to show all these steps necessarily, but now I'm going to use rule number 6, which tells us any numbers can be raised or is considered to be raised to the first power. And at that point, we're at the critical step. So we know that the exponents must be equal. And then we get x is equal to negative 13 over 8. So if you got that one right, good job. Go ahead and try number 31. You can use 28 to help you. And when you come back, we'll do it together. All right, we're back. So I'm going to use rule number 1. Sorry, the screen is going back and forth there. Because we're multiplying powers with the same base, so we just add the exponents. So we have 2 minus 3x over 5 plus x. Okay, so then we're going to simplify. There's a lot of math going on here, but you can write x as 5x over 5. And then you get 2 plus 2x over 5. Then we're going to use rule number 7 to turn that 1 into 6 to the 0 power. And now we're at the critical stage. So we can get rid of the bases, and we know 0 must be equal to 2 plus 2x over 5. And we get negative 5 is equal to x. So if you got that answer, good job. Okay, go ahead and try number 32. Use number 29 to help you. And when you come back, we'll do it together. All right, we're back. So we're going to use rule number 2, which tells us if you're dividing powers, you just subtract the exponents. So 2 to the x power, 2 to the x minus negative x plus 1. The placement of the parentheses is crucial when it comes to writing this stuff down. You're subtracting this whole thing here. A lot of students would make a mistake just on that step alone. So if you made that mistake, go ahead and go back and redo the problem. Why does it matter? Well, you're going to see why it matters in a couple of seconds here. So we're going to simplify that. 2 minus negative x, that becomes, x minus negative x becomes 2x, because you're subtracting a negative, which it makes it a positive, so it's x plus x. Again, this is a negative 1 here. You're distributing it to these two numbers, so that becomes positive x and negative 1. positive x and negative 1. So x plus x is 2x, and then b minus 1. Again, this is just all review stuff. You may be a little rusty on some of that stuff. That's okay, but if you've never seen that stuff before, then it just means that you got to go back to my beginning algebra course and review some of that stuff. So now we're going to use rule number 9 to change the right side of the equation. That's going to become 2 to the 1/2 power. And then we're at the critical stage. The bases are the same, so we can get rid of the bases. And doing the math on that, we get 3/4. X is equal to 3/4. So if you got that one right, good job. Okay, on to number 33. Just doing some more problems here. So we're going to use rule number 3 first. And you can go back and check rule number 3 if you're not sure why that worked. 4 times 5 is 20, so we have 20 to the x power. You don't really need the parentheses, but it might help to write those. I'm just going to erase them and highlight that. So 4 times 5 became 20. So now I'm going to change the 400 to 20 to the 2nd power. Now I know that's kind of tricky there that I did that, but because we have a 20 base here, base 20, we know we're going to have to change this to base 20. So that gives you a kind of a hint on what to do. So now I'm going to use rule number 8. Again, going backwards with rule number 8 to bring it, turn the fraction into a negative power, a negative exponent, and then we're at that critical stage, and we know that x equals -2. So just another example where we're solving exponential equations with the exponent rules. So now we're going to use rule number 4. And again, if you're not sure what rule number 4 is, you can just go back and review that, looking at those exponent rules. So just to be clear, 24 divided by 4 became 6. And now I'm going to use rule number 10 prime, that would be, I believe. 10 prime, just because it's a different variation of the rule. So that's going to give us 6 to the 7/6 power. And we're at the critical stage at that point. We can see that we have exponential expressions that are equal to each other. The bases are the same, therefore the exponents must be the same, equal. Okay, so I want you to try number 35, use number 33 to help you, and when you come back, we'll do it together. Alright, we're back. So I'm going to use rule number 3, just like we did in the problem above. And then we get 6 to the x power. So now that we have our base, it gives us a clue as to what we're going to do with the 36. We're going to change that to 6 to the 2nd power because now we have base 6, but the equation isn't really in the right form yet. So we're going to have to use rule number 8, which tells us to bring that up and turn it into a negative exponent, an expression with a negative exponent. And now we're at the critical stage, and we see that x is equal to -2. So if you got that one right, good job. If you made a mistake, that's okay. Just go back and figure out what you did wrong. Be aware that this is not going to be the variation of Rule 10. It's just going to be Rule 10. So Try 36, and when you come back, we'll do it together. All right, we're back. So I'm just going to rewrite the left side of the equation. And I'm going to use rule number 3. Actually, rule 4 on the right side of the equation. So that was rule 4. And 30 divided by 10 becomes 3. And again, I'm just doing this step by step here. You can do more than one step at once if you want. But I'm just trying to go slow here so you know exactly what's happening. Okay, so now we're going to use rule 10. So that's 3 to the 5/4 power. And we're at the critical stage. We have exponential expressions that are equal to each other and the bases are the same, so therefore the exponents must be equal. So if you got that one right, good job. Okay, so now we're going to equations requiring 3 exponent rules. I'm going to write that 4 as 4 to the 1 power. That's rule number 6. Then I'm going to use rule number 8 to change that to a negative exponent. And then I'm going to change that 64 to 4 to the, whoops, I forgot to write my x, sorry about that. I'm going to change that 64 to 4 to the 3rd power. And then I'm going to use rule number 5 because we have a power raised to another power. So we have to multiply those powers, so that becomes 4 to the 3 times x. And now we're at the critical stage. So we know that negative 1 must be equal to 3x. And let me find some more room here. And x is equal to negative 1/3. So you can see we used 2 rules on that problem. And you might be getting tired of writing these Roman numerals, but that helps us to understand where the stuff is coming from. We're not just getting these operations out of nowhere. Okay, now I'm going to use rule number 4. So that becomes 25 over 5, all raised to the x plus 2. And the reason I can do that is because these x plus 2's are the same. If they weren't the same, then I couldn't do that. I would have to solve the problem in a completely different way. Now, I think I may have to do multiple steps at once here. We'll see how this works out, because I don't know if I'm going to have enough room. In fact, I probably won't. So I'm going to go ahead and use rule number 10 there as well as rule number 4. So I used 4 and I used 10. Actually, no, I'm sorry, that's 9. And then we're going to divide 25 by 5 to get 5 to the x plus 2 power. And we're going to use rule number 2, because we're going to subtract those powers, and we get 5 to the 1/6 minus 3. Subtract those exponents, that is. We have the same base, powers with the same base, subtract the exponents. And then we get 5 to the x plus 2 is equal to 1/6 minus 3. That's going to be negative 17 over 6. And so now we're at the critical stage where we can get rid of the bases. Sorry, we're kind of losing room here. And you can go back to my beginning algebra course to review how to solve an equation with fractions. This would be 12 over 6. Subtract that from both sides, and you get negative 29 over 6. A lot of different ways to approach a problem where you have fractions. Okay, so let's try number 39. Try one more of these 3-rule problems before you try one on your own. Okay, so I'm going to use rule number 10. This is different. We have a variable here, but that's okay. It's still rule number 10. So that's going to be 7 to the x over 3 power times 7 to the 5x minus 5. And then I'm going to use rule number 1. For multiplying powers, we add the exponents if the bases are the same. So we have 7 to the x over 3 plus 5x minus 5. And then I'm going to use rule number 7 to change that 1 to a 7 to the 0 power. And x over 3 plus 5x is going to be 16x over 3. Again, that's just basic math. You can go to my previous courses if you want to review that. And then we have that critical stage. 0 is equal to 16x over 3 minus 5. And that's going to be 15 over 16. So these are problems that require 3 rules. Notice we use 3 rules in all these problems. So I want you to try number 40. Use number 37 to help you, and when you come back, we'll do it together. All right, we're back. So I'm going to change 5 to 5 to the 1 power. That's rule 6. Then I'm going to bring that up and make it 5 to the negative 1 power. That's rule number 8. Exponent rule number 8. Then I'm going to change 25 to 5 to the 2nd power. That's not really a rule. We're just changing the form of that. And now I'm going to use rule number 5. Raising a power to another power, you just multiply the exponents. And now we're at the critical stage where the bases are the same and the powers are equal. So we can get rid of the bases, and x is equal to negative 1/2 just using basic algebra. Okay, so we used 3 rules there. If you got that answer, good job. Try number 41. Use 38 to help you, and when you come back, we'll do it together. All right, we're back. I'm going to use rule number 4. That gives us 27 over 9, all raised to the x power. Then I'm going to use rule, I'm going to simplify this part, so that becomes 3. And I'm going to change the denominator to 3 to the 1/4 power. That's rule number 9. And I'm going to use rule number 2. We're dividing power, so we can, because we have the same base, we can just subtract the exponents. And 6 minus 1/4, that would be 23 over 4. Again, you can go back to my arithmetic course if you're having trouble subtracting a fraction from a whole number. This just becomes 24 over 4, and minus 1 over 4 is 23 over 4. So then we have 23 over 4 is equal to x, because this is the critical stage. All right, if you got that one right, good job. That was a challenge problem. Go ahead and try 42. Use 39 to help you. And when you come back, we'll do it together. All right, we're back. So let me move this over a little bit. And what should we do first? I think we'll use rule number 10. And I think that's the variation of rule number 10. So that would be 2 to the x over 5 power. Actually, no, that's not the variation. That's just rule number 10. 2 to the x over 5 power. And now we're going to use rule number 1. Actually, no, we're going to use rule number 3. Why? Because these powers, those exponents are the same. So we can just put the bases together. That doesn't happen very often, but it does happen sometimes. And 2 times 10 is 20. So again, I got that from there. And we can change now that we know what the basis is going to be, we can change that 1 to 20 to the 0 power. And I can probably space this out a little bit more. So now we're at the critical stage. And we know that x over 5 has to be equal to 0. And therefore x must be equal to 0. Multiply both sides by 5, and we see that x must be 0. So if you got that answer, good job. Now we're going to review classifying numbers. We classified numbers previously in this course. We're not really going to review this stuff much. We're just going to review irrational numbers. An irrational number is a non-terminating, non-repeating decimal. So pi is an example of that. If you write pi in decimal form, it would be 3.14, and it would never stop. It would keep going on and on and on. That means it's non-terminating. It doesn't stop. But there's also no pattern to these numbers. In this example here, 0.833333, that's a non-terminating decimal, but it repeats because the 3's just keep repeating. But pi is an irrational number because not only is it non-terminating, it never stops, but there's no pattern, there's no repeating pattern. So that's why we have to use a symbol. We use the symbol pi to represent that irrational number because we can't write the full number. We have to always approximate it because it just keeps going on and on forever. Well, that's going to help us to learn logarithms. So now we're going to do an introduction to logarithms. We solved exponential equations like so in the first part of this class, and we learned that you can just change 8 to 2 to the 3rd power, and obviously x would then be equal to 3. Very easy. So with that problem, we can easily do it in our heads. Sorry. But what if I change this 8, this blue 8, what if I change that to a 7? Then if we try to calculate that number, you're going to find it's not very easy. And some students might say, well, that number doesn't exist. There is no number you can raise this to get 7. But it turns out that there is a number you can come up with that is kind of theoretically it's an exact number, but we can come up with an approximation for that number, and you don't really have to know how to calculate that number because the calculations are really convoluted and complex. So you're not really required to know, but we are required to come up with symbols to represent that number, just like we came up with pi, for example. Remember, pi represented an irrational number, 3.14, that goes on and on and on. Well, we're supposed to come up with a symbol just like we came up with a symbol for pi, and that symbol is called log base 2 of 7. And there are different ways to state that, but the most popular way these days is log base 2 of 7. This also tells us what to enter into the calculator, or at least it gives us an indication of what to enter into the calculator. So there's a lot of different ways to do this. You can use your iPhone. I'm going to go ahead and use the built-in calculator on Windows 10. And what you're going to do is you're going to push the second button at the upper left. See that second button that I just pressed down there? And it's blue now. And then I'm going to push on the keyboard, I'm going to push 7. And I'm going to push at the bottom left, see this log base y of x? I'm going to push that. And then I'm going to push the 2, base 2, and then equals. And I get 2.807, or we're going to have to round up, so that's 2.8074, and I'm going to have you round to the nearest 10,000th place when you do these problems. So this symbol, this symbol here represents the exact number. But if you're going to actually approximate it, you have to use a calculator. Enter this into your calculator, and you would get this approximate answer. But again, this is an irrational number, so it just goes on and on and on and on. And again, you might think, well, I want to know how to calculate this. Well, again, the operations are really convoluted, and if I took 100 engineers and scientists, I would be shocked if one of them could explain how to actually do this calculation. It's not that they're not capable, it's not that you're not capable, it's just you're not required to know how to do this. So in this example, when you have an equation like this where the answer is not obvious, you would just use a calculator. And, you know, this answer makes sense because isn't it true that 2 to the second power is 4, and 2 to the third power, as we saw up there, is 8. So we have 8 and we have 4, but we don't want 4 or 8, we want something in between. So it makes sense that the blue powers, you know, our number that we're looking for down here, that should be in between those blue numbers, and it turns out that it was. So it makes sense. And a lot of students, they really don't like this notation. It makes them nervous, primarily because they don't know where we got that number. But again, you're not required to know. It's like when you use trigonometric notation. For example, sine 40 degrees. We learned this in my geometry course. If you forgot that, that's okay. But this is another example where the calculations are really convoluted, and you're just not required to know how to do that without a calculator. So this is another example of that, where you just enter it into your calculator. So a lot of students get intimidated with this type of notation, but please don't get intimidated. It's just a way to enter, to find the answer, an approximation to the answer in your calculator. So now I should also mention that, you know, you can use log notation with this example also. You can say x is equal to log base 2 of 8, and you'll get 3. The only difference is this is going to be a rational number, whereas down here you see we got an irrational number. So log notation works even if the answer is not irrational. And so here's the notation that we use. If b to the x power is equal to c, then you enter log base b of c into your calculator to find that exponent x. And, you know, we don't really have to discuss this in detail now, but just be aware that traditionally, when you use log notation, neither c nor b are allowed to be negative in this logarithmic notation, this expression here. And, you know, we'll talk about that more later. That's kind of, it's not exactly obvious why that would be true, that those numbers can't be negative, but again, we'll get into that later. Okay, so now we're going to do some practice. So we're going to write the solutions of the equations below using log base b of c notation. Then we're going to use the log base y button on your iPhone to approximate the answers to the nearest 10,000th. If you don't have an iPhone, then you can use the calculator on your Windows computer like I did in the previous problem. Or you can search logarithmic or logarithm calculator on your web browser. Also, there are free graphing calculators on the Google Play Store, and if you have a graphing calculator, an actual graphing calculator which looks something like this with a big screen like that with a lot of buttons there, that probably has the capability of doing that somehow. And if you have a Casio scientific calculator which has a smaller screen with a lot of crazy buttons here, it'll probably have a button that looks like this, and you can just enter in those numbers. That's the easiest way to do it. But TI scientific calculator, that's the scientific calculator that I was just mentioning, the Casio one. The TI Texas Instruments scientific calculators, I don't think they have that capability. Just be aware, read here in red, just be aware that some devices will calculate base 10 logarithms and base e logarithms, but no other base logarithms. For example, I think the built-in Android calculator will only do base 10 and e, I believe. Last time I checked, but I might be wrong about that now. So anyway, those are just some different ways to calculate these answers. So here we have 5 to the x equals 9, and you can see, if you think about this, the answer is not obvious. If you have 5 to the 1 power, that equals 5. If you have 5 to the second power, that equals 25. But we don't want 25, and we don't want 5, okay? We want 9, which is in between those. And so we know that our answer is going to be somewhere in between 1 and 2. So let's see what the answer is going to be. First, we're going to write a symbol that represents the exact number. That's going to be log base 5 of 9. So that's part of our answer. That's what we're supposed to do, is write the answer in log base b of c notation. But now we're actually going to use a calculator to approximate what that would be. That number is going to go on, and it's never going to stop. It's a non-terminating decimal and non-repeating decimal. Now, again, you can use your Windows calculator, but I'm going to show you how to use the iPhone. Start your calculator on your iPhone, your built-in calculator, put it, rotate it in landscape mode, and you're going to push the second button at the upper left, and then you're going to push 9 on the keyboard, and then you're going to push the log base y button, and then you're going to push the 5 on your keyboard, and then equals, and then we have 1.3652. We're rounding to the nearest 10,000th place, which is the 4th decimal. So there you go. That's an estimate there. And so let's try number 44. Now you can write x over here and then equals, or you can write x over here and then equals. I'm going to do it that way because this equation is kind of turned around, but it doesn't matter which way you do it. The only thing that matters is that base is the little number right next to the log notation, and then you put the 2 there, and be sure that the 2 is bigger than the base. The base is always written as a kind of a subscript next to the log notation. So that is the answer. That is the symbol that we use to represent the actual answer. But if we want to calculate it, I'm going to do it on my iPhone again. I'm going to write 2, enter 2, and then log base y, and then 3, and then equals. And I get 0.6309. So there you go. So again, to use an example here, let's say that we had 2 to the x power equals 8. Well, we could say that x equals log base 2 of 8. And if we enter that into the calculator, we just get 3, because that would be an easy equation, you see. Problem is we don't have that. We have 17 to the x power equals 8. That's not easy. In the previous problem, we didn't have to use log notation, but we could. But here we have to use log notation because this is just going to be a number that's non-terminating and non-repeating. It's going to go on forever. So we have to use this log notation to write a symbol for the exact number. And if we want to approximate the number, we have to use our calculator. We're pushing 8 log base y, then 17 equals. So x is approximately equal to 0.734. And if you're a little rusty on rounding, you can go back to my rounding class in my arithmetic course. Here we had to round up quite a bit, so there ended up, even though we're rounding to the nearest 10,000th place, we only have 3 decimals there. Okay, let's try one more of these before you try one on your own. So again, you can put the x on either side here. Don't let me flipping these equations around confuse you. So that's the exact answer written with a symbol. I want to make that g a little smaller so it doesn't run into the other answer. So that's the exact answer, but if we want to approximate the answer with an actual number, I'm going to press 100 in my iPhone keyboard, then log base y, then 91 equals, and we get 1.0209. All right, so again, the most important thing is to know that that 91 goes there. That's the small number that goes, it's a subscript of this, log notation. If you confuse those, if you put the 91 here and the 100 there, then you're definitely going to get the wrong answer. So go ahead and try number 47. Write the exact answer as a symbol, and then write the approximated answer. So try 47. When you come back, we'll do it together. All right, we're back. So x is equal to log base 7 of 6. And if we approximate that using the iPhone, we have 6 log base y, and then 7 equals, and we get 0.9208. So we got that answer. Good job. Okay, try number 48, and when you come back, we'll do it together. All right, we're back. It doesn't matter what side you put x on, as long as the base is 6, that little number, and the big number is 20. So that's the exact answer written as a symbol. But if we want to know the actual numbers that represent the real answer, or at least an approximation, we have to enter 20 into our iPhone, and then log base y, and then 6, and then equals. And I want you to understand that it really depends on the calculator that you're using. Sometimes you enter this first and then these numbers. Sometimes you enter this number, then your log button, then 6, which is what we're doing in the iPhone. So it depends on your calculator, and it can be very confusing figuring out how to enter it in. But when you compare what you're getting with what I'm getting, it shouldn't be hard to figure it out. So if you got that answer, good job. Why don't you try number 49, and when you come back, we'll do it together. All right, we're back. X is equal to log base 8 of 10. That's the exact answer written as with a symbol. But then we want to approximate the answer, so I want to plug in 10 to my iPhone, then log base y, then 8, then equals. And remember, you got to be pushing the second button on the upper left of your iPhone to get to the other keyboard. So if you got that answer, good job. Why don't you try number 50, and when you come back, we'll do it together. All right, we're back. Again, the x can go on the left side or the right side. It doesn't really matter. X equals log base. Just make sure you put the 2 there and the 5 there. Don't mix up those numbers, or else you get the wrong answer. So then x is approximately equal to 2.3219. So if you got those 2 answers, good job. Now we're going to do some additional types of exponential equations, some different varieties. And we're going to use what we learned about logarithms. So determine if you can solve the following equations without a calculator. If you need a calculator, write the solution in log base b of c notation, and then use a calculator to approximate the answer to the nearest 10,000th. And of course, write the Roman numeral of each exponent rule that you use. So what we're going to do is we're going to first isolate this exponential expression. Again, these are just different varieties of exponential equations. And we're going to get rid of the 2 and the 9 in order to isolate it. Remember, isolate means get it by itself on one side of the equation. And so we're going to subtract 9 from both sides. And at this point, it's important to understand, because a lot of students have trouble with this expression over here. It's important to understand that the 2 is multiplied into this whole expression in blue. So the yellow 2 is multiplied by the blue 6 to the x power. So we need to divide both sides by 2. So we divide 72 by 2 and we get 36, and we divide this expression by 2 and it gets rid of this 2 here because, again, the 2 is multiplied. So the opposite of multiplication is division. Now I do have to warn you that a lot of students will take this expression and they'll say we can just multiply the 2 and the 6 to get 12 to the x power. Well, we can't do that because these expressions, if you write 2 to the 1 power, you can see that they don't have the same base. And even if they did have the same base, you would add the exponents, not just write the x kind of randomly. Now, if you had an expression that said 2 to the x power times 6 to the x power, then you could go ahead and multiply and get 12 to the x power. That's rule number 3. But this 2 doesn't have an x. So I know that these exponent rules are very complicated, but you're going to get the hang of it as you use them more and more. So at this point, the question is, do we need a calculator? And obviously we don't, because you can just write, you can write 36 as 6 to the second power, and then x is equal to 2. That's the critical step. So we did not need a calculator on that problem. That was a different variation of an exponential equation, and we did not need a calculator. So let's try number 52 and see if we need a calculator on that one. So again, we need to isolate this exponential expression, which means we need to put the 3 and the 5 on the other side of the equation. So I'm going to add 3 to both sides of the equation. And then I'm going to multiply both sides by 5. This is 10 to the x power divided by 5. If you want to get rid of the divided by 5, you multiply both sides by 5. I know this is very basic stuff, but a lot of students have trouble with some of the basic stuff sometimes. So I'm trying to be I'm trying to do something very unusual for an intermediate algebra teacher. I'm going back and showing you some of the stuff that you may have forgotten. A lot of teachers don't do that. They just say, you should know it. But remember, we can't review every single thing in this course. That's why the previous courses are prerequisites for this course. So at this point, do we need a calculator? And of course, the answer is we don't, because we can use rule 6 to change 10 to 10 to the first power, and we see that x is equal to 1. So we did not need a calculator on that problem, and that was the critical step there. But in the next problem, we are going to need a calculator. So you're going to see what's going to happen here. We're going to subtract 4 from both sides, and we get negative 12 on the left side of the equation. And then we're going to divide both sides by negative 4, and we get 3 is equal to 8 to the x power. At that point, we need to stop and think, there's something weird going on here. So I'm going to color that blue. You see the green, we did not need calculators for these. But with the blue, it seems that we do need a calculator, because think about it. What do we raise 8 to? What power do we raise 8 to get 3? Well, it's just not, it's not easy. We need a calculator. So what do we enter into the calculator? Well, we enter in log base 8 of 3. That's the exact answer written in symbolic, or it's a symbol. It's a symbol for the exact answer, like we write pi, for example. So that's part of the answer, because remember it asks us to write the solution in log base b of c notation, so we have log base b of c notation. So that's the exact answer written as a symbol, but now we need to find the actual quantity, numbers representing the actual quantity. So I'm going to open my iPhone app, and you can use, or my calculator app on my iPhone. You can use whatever calculator you want to use, but I'm going to put it in landscape, rotate it in landscape, and press the second button at the upper left. Remember, you have to change the screen. Then we push 3, and then the log base y button towards the middle, and then 8, and then equals, and we get 0.5283. So we're rounding to the nearest 10,000ths place, which is here. And this time we rounded down. So you might want to take a screenshot, or better yet, a picture with your phone, because you're going to be doing some of those problems now. So I want you to go ahead and try number 54. And again, we're trying to isolate the exponential expression by getting rid of the 2 and the 1. And if you need a calculator to figure out the arithmetic, because we have that decimal, that's fine. It doesn't really make a difference. You don't really need a calculator. You can probably do it in your head. But the key is, do we need a calculator to use the log function? So try number 54, and when you come back, we'll do it together. All right, we're back. So I'm going to subtract 1 from both sides of the equation. (1.5) minus 1 is 0.5. You really shouldn't need the calculator for that, but if you used it, that's okay. But this part, you might need the calculator. We're going to multiply both sides by 2. Why? Because this is 5 to the x power divided by 2. If you want to get rid of the 2, we have to do the opposite of division, which is multiplication. Again, this is just basic algebra. And 2 times 0.5, if you do that in your calculator, you get 1. But again, this is just 1/2, so if you multiply it by 2, obviously you're going to get 1. I know that this is very basic stuff for intermediate algebra, but a lot of students may have trouble with that basic arithmetic. At this point, do we need a calculator? Well, if we change that 1 to 5 to the 0 power, you can see, and that was rule number 7, you can see we don't need a calculator. X is equal to 0. So if you got that answer, good job. That's the critical step there. So we did not need a calculator for number 54. Try number 55, and when you come back, we'll do it together. All right, we're back. I'm going to subtract 6 from both sides, and I get 16. And then I'm going to divide both sides by 2, and I get 8 on the right side of the equation. And at that point, do we need a calculator? Or can we do it in our heads? Well, what do we raise 9 to get 8? That's not very simple. If we had 9 to the x equals 9, that would be pretty simple. X would just be 1. If we had 9 to the x power equals 1, that would be pretty simple, because it would just be 0. X would be 0. We did those problems previously. And if we had 9 to the x power equals maybe 81, then that would be easy, because we could just change 81 to 9 squared, and x would equal 2. But we don't have that situation. We have 9 to the x equals 8. That's not easy to calculate, so we're going to have to use our calculator. But what do we enter into our calculator? Well, we enter in this symbol, log base 9 of 8. So that is the exact answer written with a symbol. But we also have to give an approximation for the actual quantity that we're looking for. So I'm going to use my calculator. I'm going to press in 8, then the log base y button, then 9 equals, and we get 0.9464. 9464. And we rounded to the nearest 10,000th place. So if you got those answers, good job. So this blue part here told us that we need to use the calculator. And again, what do we enter into the calculator? We enter in that notation there. That's the purpose of this notation, is to just know what to enter into the calculator. There are other uses for it that we're going to learn in the next class, but for now, that's all you have to know, is we use that notation for the calculator to calculate irrational number. This is an irrational number. It's a non-repeating, non-terminating decimal. Go ahead and try number 56, and when you come back, we'll do it together. All right, we're back. Add 10 to both sides, and you get 42 over here. Divide both sides by 7, and we get 6. And the question is, do we need a calculator? Well, it's pretty obvious that we do. What do you raise 3 to get 6? I mean, that's not very easy. So how do we, what do we enter into the calculator? Well, we enter in log base 3 of 6. So that's the exact answer written with a symbol. But if we want an approximation, then we need to press in 6 in our keyboard, then log base y, then 3, then equals, and we get 1.6309. So that's an approximation of the answer. So if you got those answers, good job. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1 and screenshot number 2 and screenshot number 3 and screenshot number 4 and screenshot number 5 and screenshot number 6. But don't go before you get your homework. Just take a look at the homework. Here's screenshot number 1 and screenshot number 2. You have the answers there. Don't forget to check all your answers. Remember, your homework has to have 4 characteristics. It has to be complete, correct, neat, and in proper chronological order in your binder. And remember, if you don't do that homework, it's a 100% guarantee you're going to learn absolutely nothing in this entire course. So get that homework done, and I'll look forward to seeing you in the next class.